Hello, our topic today is for B, logarithms in base A. If you guys recall what we learned in 4A, the topic in 4A is logarithms in base 10. So the only difference between these two lessons is we change base 10 to any base A. So let's look at. We can use the same principle to define logarithms in other bases. For example, if I have a function f of x equals a to the power of x, as long as this a is larger than 0 and cannot be 1, so the base right now is more general case. It can be 2, 3, 10, 100, 0.1, 1/2, 1/3, etc. Then f inverse of x is log ax. So it's exactly the same as what we learned in 4a. So, but anyways, if we want to find the inverse of this original exponential function, we interchange x and y. So we will have x equals a to the power of y. Then we solve for y. So this y is in the exponent. And we have already known that Jean Napier was the first person to propose the use of the logarithm. With this log symbol, we can bring this y down from the exponent. So we will have y equals log ax. So this y is this exponent y here. So let's look at the graph. Let's just suppose in the original function, this base a is greater than 1. Let's graph its inverse. So we all know that the inverse function of the original function should be reflected over in the line y equals x. So I will still graph y equals x line. When a is larger than 1, this exponential function should have the reflection image look like this one. So they are reflected over the line y equals x. The original function passed through 0, 1. This inverse passed through 1, 0. And its function expression is y equals log x base a. If in the original function, the base a is between 0 and 1, we know the graph is a decreasing model. So it looks like this one. The inverse of this blue graph, of course, is still reflected over in the line y equals x. But the reflection image will look like this purple one. So it's y equals log ax, but this a should be between 0 and 1. Okay, so given x equals a to the power y, we define the variable y as follows. Y equals log x and this base a. So of course you guys know how to read this log notation already. This one is read as y. So this one is read as y is the logarithm of x in base a. Or we can say y is the logarithm of x to the base a. Either of the way is fine. So we have already known this one in 4a. So even we change base 10 to base a, as long as the base is larger than 0, cannot be 1. So this one is the exponential form, which is mathematically identical to y equals log x to the base a. And this y becomes logarithms. So right now, this become a very basic skill. You guys need to know how to convert and the exponential form to the log form and vice versa. So let's look at it. This is the exponential form and this exponent 3, which is the y. So this one is the base. And we know this one is called argument in the logarithm, which is also the value of the power. So its log form will be 3, the exponent, equals log base 2, argument 8. So just like what we learned in 4a, the exponent is the logarithm. The logarithm is always the exponent in the exponential form. So here, if we are given the log form, this exponential form will be the base is 5 and the log value is 2. This 2 is the exponent equals the argument. And you guys will see 5 squared equals 25. This exponential form really makes sense to us. So two log identities. It's the same as the base 10 log. If you guys still remember the two identities we learned in 4a. So here, they are exactly the same. We still can use the same way to derive these two log identities. It's because x equals a to the power y. This one is mathematically identical to y equals log ax. So if I use this a to the power of y to replace this x in the log form, we will get to the first log identity. If I use this y, which is log ax, to replace the y in the exponential form, I will get the second log identity. Okay, so right now, the first skill we need to know is to convert between the exponential equations and the log equations. Example 1. Express 5 to the power 4 equals 625 in logarithm equation. So we know this 4 exponent is the logarithm. So remember, exponent is the logarithm. Vice versa, the logarithm is always the exponent. So 4 is the y value equals log base 5 argument the power value 625. So I hope you guys can try all those 4 questions yourself. Let's look at how we can convert each of them to the log equation. So this one, the exponent is 2 and the base is 7. So the 7 is still in the base of the logarithm. Argument, power value 49. So if you always can remember the exponent is the logarithm value, which is the y value in the log equation, so you should have no trouble. And the base is always the base. Power value is the argument. So here we will know 1/3 equals log base 8 argument 2. Okay, let's look at number 3. Make sure that you know how to identify which one is the exponent. Which one is the exponent? -3. So -3 equals log. So -3 is the log value. Which one is the base? 5. And the power value, which is the argument, 125. 1 over 125. Okay, so number 4, this one is a little bit tricky because we have 4 times 9 to the power of x equals a. So I have a number times a power. I don't like this number 4 in front of the power. So if you don't like this number, you can divide both sides of the equation by 4 first. So in this case, this 4 divided by 4 can be cancelled out. So I will only have 9 to the power of x equals a over 4. Then I only have one power on the left side. And this is the power value. So my exponent x is the log value. So x equals log, my base is 9. A over 4 is the argument. Okay, so right now, of course, we need to know how to convert the log form back to the exponential form. So let's look at example 2. Express log 81 in base 3 equals 4 in exponential form. 4 is the logarithm value. And we talked about this one already. The logarithm value, or the logarithm, is always the exponent. So when I convert this one back to the exponential form, 4 is the exponent. I put it in the exponent. Which one is the base in the exponential form? The base is always the base. No matter it's in the log form or in the exponential form. So 3 is the base. 3 to the power 4 equals 81. You can use your exponent knowledge to double check whether the exponential form makes sense to you. So 3 to the power 4 equals 81. It really makes sense. Okay, so I want you guys try to convert each log equation back to the exponential form. So here, log is the exponent. So 2 to the power 5 equals 32. 4 to the power of negative 1 equals 1/4. 10 to the power of negative 2 equals b over 2. X is the base, y is the exponent. X to the power y equals b over a. Okay, that's how we can change the log equation back to the exponential form. So right now, we need to look at how can we find the log values. So example 3. Let's find log 216. We have 2 different methods. One method is we can use the idea of converting a log equation to the exponential equation form. The second method is we can use the log identity. So let's look at what is the first method. So the first method, I will let y be the log value. And you guys know this y is the log value, which is the exponent in the exponential form if you convert this one to the exponential form. So it's 2 to the power y equals 16. How can I solve for y in this exponential equation? I convert 16 to a power of 2. So right now on both sides of the equation I have a common base 2. Then I can ignore the base. Their exponents should be the same, which means y is 4. That means the original log value, log 216, is 4. Okay, so this is the first method. We use the skill of converting a log equation to the exponential equation and find the log value. The second method is we know this identity. The identity is y equals log. So I have a log, the base is a, and in the argument I have a power. The base is still a, so it's a to the power y. So I will find that this log value is just the exponent y. So what I will do is, for log 216, I change this 16 to 2 to the power 4. So log 2 to the power 4, the value is just 4, which is the exponent in the argument. So this y equals the y. Okay, so right now I hope that you guys can have a try to find the log value in b. So log of 5, 0.2. So you still can let y be log of 5, 0.2. So I convert this one to the exponential form, which is 5 to the power y equals 0.2. Think about what is 0.2. Convert 0.2 to the fraction, which is 1/5, equals 5 to the power y. And then look at 1/5. We all know this one is 5 to the power of -1. So equals 5 to the power y. So we find that I have two powers with the same base equal. That means their exponents should be equal. Y equals -1. Okay, so the second method is I use this log identity here. I will convert log of 5, 0.2, especially this 0.2, to this fraction. And this fraction is the same as 5 to the power of -1 with the negative exponent. So this one, exponent, if I have a logarithm, the base is 5, and in the argument, I have a power, the base is still 5. So the log value is just the exponent in the argument. Okay, I hope that you guys can use either of the methods or both of them to find C and D values. So let's look at number C. It's exactly the same. I will let y be log value. Then the second step is convert this log equation back to the exponential form, which is 10 to the power y equals the 5th root of 100. Convert the right side, the 5th root of 100, to a power of 10. So this one is 100 to the power of 1/5. Let's get rid of the radical. And this one, 100 is 10 squared. So I can convert this one to the power of a power. So then I multiply the exponents, which is 10 to the power of 2/5. So here, the last step is both of them have the common base 10. I ignore the base. That means the y value is 2/5. Of course, you also can find this 2/5, which is this log value, from this log expression directly. So I change this one, especially, of course, the argument to a power of 10, which is 10 to the power of 2/5. If you don't know how to change this 5th root of 100 to 10 to the power of 2/5, look at all the steps we went through here. They have exactly the same process for the conversion. So anyways, right now, this one is 2/5. Okay, so the last one, it's exactly the same. I will let y be log value. And convert this one to the exponential form. It's 2 to the power y equals 1 over root 2, which is the argument. I will convert this 1 over root 2 to a power of 2. So it's 1 over 2 to the power of 1/2. This is 2 to the power y. And we all know 1 over 2 to the power 1/2 is the negative exponent in the single power. So 2 to the power y. So that means this y is -1/2. Of course, you still can just convert this argument to a power of 2. So it's 2 to the power of -1/2. So this is the reason we can know the log value is -1/2 based on the log identity. Okay, so the lesson is over here. I hope that you guys can do some practice to help you get familiar with the connection between the log equation form and the exponential equation form. And you know how to use the identity to find the log value as well.